Okay, so in this video, we're going to be deriving Bernoulli's equation through the use of Reynolds Transport Theorem. And I'll start by saying Bernoulli's equation is one of the most powerful equations in fluid mechanics and engineering more broadly. However, it's also one of the most misused equations in engineering. And what I mean by that is there's a very specific set of assumptions that needs to be satisfied before you can use Bernoulli's equation properly. And if those assumptions are not satisfied, then the equation can give you very misleading results. So we're going to go over the derivation of Bernoulli's equation, we're going to go over the assumptions that need to be satisfied to use it, and we're going to go over some stereotypical example problems that you can apply Bernoulli's equation to. Okay, so to start, we're going to look at this top left geometric diagram here, and we see that we have kind of this prismatic chip that expands outwards like this. And these red lines are streamlines, and we can see that here our blue dotted line is our control volume. So in control surface 2 here and control surface 1, we have streamlines going across those two planes. So we have streamlines going through control surface 1 and through control surface 2. These other control surfaces, so these side planes, this top plane, the bottom plane, etc., those planes bound the streamline. So there's no streamlines crossing those planes. The streamlines are only crossing control surface 1 and control surface 2. So on control surface 1, we have an area A, a density rho, a velocity Vs, and a pressure P. On control surface 2, we have an area A plus dA, a density rho, a velocity Vs plus dVs, and a pressure P plus dP. We can see that we have differential changes in our velocity, pressure, and area, and that's because, as we'll see, the length, the axial length of this prismatic chip is also differential. So if we kind of spin this prismatic chip to the left and look at it from the side, you could see that it's angled upwards a little bit as well at an angle theta to our global coordinate x. And our gravity is acting anti-parallel to our positive coordinate z. The length of this prismatic chip from the side is ds, and that is along our s-axis, which is the axial axis of the prismatic chip. So you can see the s-axis goes right through the chip, and the length of this prismatic chip along s is ds. Now, if you kind of look at control surface 2 here, and you kind of zoom in, you'll see that we have our area A plus dA, and that is composed of 3 sub-areas. We have this first orange area, this second orange area, and this primary red area. This primary red area is of area A, and these orange areas are both of area H times dW. You can see that this is dW, this is dW, and this is H. So we have this orange area is H times dW, this orange area is H times dW, and this red area is A. And so each of these orange areas is therefore dA over 2. Now, if you look at control surface 1, which is this control surface right here, and again, control surface 2 is this one. If you look at control surface 1, you'll see that we have our red area A, and that is equal to H times W, right? So our control surface 1 has area A, and our control surface 2 has area A plus dA. And if you kind of look at a top normal view of this prismatic chip, it kind of gives you a more zoomed in look at these streamlines. So you can kind of see that here are orange areas associated with control surface 2. So here's our dA over 2, here's our dA over 2. These are the orange areas associated with that, and here's our area A, which kind of projects all the way from control surface 1. We also have our coordinate axes here. We'll kind of get into why these are important, but we have our global coordinate axes, x, y, and z, and then we have our local coordinate axes, our n, s, and o, kind of associated with our s-axis, this s-axis right here. Our normal axis, which is perpendicular to that, is still our Cartesian coordinate system. So our normal coordinate axis is just normal to s, and then we have our orthogonal axis, as we say, our o-axis, which is also orthogonal to n and s, right? So to begin, we will look at our assumptions. And a lot of these assumptions also are not going to make sense at first, but they will make sense over time. And I just wanted to encapsulate them in one area. So our first assumption is that we have an incompressible and isothermal flow. What does that mean? That means our density is effectively constant. And that's why we have rho in control surface 1 and rho in control surface 2. And we'll see why that's important in the derivation. 2, we're going to assume that we have a frictionless flow. That's incredibly important. And this is typically where Bernoulli's equation is misapplied. If you apply Bernoulli's equation to a system with a significant degree of friction, so perhaps a system with a very low Reynolds number or with a lot of entropic losses, Bernoulli's equation will give you the wrong answer. So you can only apply to systems that are reasonably frictionless, and we'll get into what that means. 3, we're assuming that the system is steady, so none of our field variables are changing with time. 4, we're assuming that our control volume is bounded by streamlines. We've gone over what that means. 5, we're assuming our pressure and velocity is uniform at control surface 1 and 2, so we don't have to worry about a distribution, a surface distribution at control surface 1 or 2, so our surface integrals are easier. We're assuming that our pressure is uniform on the lateral sides of the chip. Again, we're assuming that our pressure on this lateral face and our pressure on this lateral face is uniform, so we don't have to worry about distributions on the lateral faces either. We'll get into that. And we're assuming that we have no body forces except for gravity, so no magnetic fields, no electric fields, nothing like that. Okay? So to begin, we're going to start with Reynolds Transport Theorem, the conservation of mass variant. And that equation is right here. And effectively it says the time rate of change of mass in the control volume plus the net mass flux through the control surface is equal to 0, right? And in another video, we will go into kind of the specifics of Reynolds Transport Theorem and the ins and outs and intuitions and assumptions underlying that set of equations. But in this video, I'll just assume that you are familiar enough with Reynolds Transport Theorem to follow this as I've laid out here. So again, the equation is as we have shown here. And since we have a steady system, our time rate of change term goes to 0. And effectively, our conservation of mass just comes down to this term, which says our net mass flux through our control surface is equal to 0. So how do we break up this integral? Well, we could break up this integral as we have here. Again, we know that mass is only flowing across control surface 1 and control surface 2. There's no mass crossing the lateral or top and bottom faces. So our integral over the entire control surface is really just an integral over control surface 1 and control surface 2, because you could see here that in our integrand, we have a v dot dA. Our v dot dA on those surfaces where there is no mass flux across is equal to 0, because the cosine of 90 degrees is 0. So this control surface integral is only going to be non-zero on surfaces where there is mass flux across, and we only have mass flux across on control surface 1 and control surface 2. So you can see that when we break up this integral, we have control surface 1 and control surface 2. So we have the integral over control surface 1 is rho 1 v1 dot dA1 plus the integral of control surface 2, rho 2 v2 dot dA2. If you look at control surface 1, what is the velocity there? It's Vs. What is the area there? It's A. And what's the density there? It's rho. Our unit normal area is facing opposite our velocity vector at control surface 1. So you can see in control surface 1, our velocity is going in, and our unit normal is facing out. So our dot product is negative. So that's where our negative rho VSA comes from. Here on control surface 2, you could do the same exact thing where you have essentially rho VSA, except now, because we're at control surface 2, it's rho VS plus DVS times A plus dA. And the reason there's no negative sign here is because when you go to control surface 2, our velocity is in the same direction as our unit normal area outwards. So the dot product is positive. So in that case, we have a plus. So it's rho VS plus DVS times A plus dA. So this is a positive quantity here. Now, if you end up simplifying this, you end up distributing these terms, you end up getting this equation right here. So I won't go over the algebra, I'll just show it. You get this equation right here. And this equation simplified is as displayed and highlighted in green. And intuitively, this doesn't really mean too much to us in the moment, but we will see that we're going to need this equation right here, which is effectively our differential conservation of mass. Our conservation of mass across our control volume as we've drawn it is described mathematically by this equation. And we'll see that we use this equation to simplify our future application of Reynolds Transport Theorem, and we'll go into that right now. So if we look at Reynolds Transport Theorem for Newton's second law, so before we looked at it for conservation of mass, now we're going to look at it for Newton's second law or the conservation of linear momentum. You can see it's a little bit more complicated now. So Reynolds Transport Theorem for Newton's second law effectively says that the net overall force on the control volume, which you could break down into the total outer surface force on the control volume plus the total outer body force on the control volume, is equal to the time rate of change of linear momentum in the control volume plus the net momentum flux through the control surface. What we kind of need to do here before we break down this equation is, let's look at our velocity vector, right? So if we look at our velocity vector, and we're looking at this in our local coordinate system, our velocity vector v will have an s component, an n component, and an o component. And that comes from, again, we're working in this coordinate system right here, where we have this s axis, and then we'd have our n axis, then we have an o axis, etc. So we'll have an S component, an N component, and an O component. And in the same way, our net force on the control volume will have an S component, an N component, and an O component. And we just have this subscript N to denote that that is a component of the net force. And it's worth mentioning that this F is the external net force on the control volume. We're not looking at internal forces to the control volume. We're only looking at external forces, or the net external force. So now what we're going to do is we're going to break up this equation, because it's a vector equation, into 3 components. So you can have an equation for each component of your vector, right? Since we're working in Cartesian space, we have 3 components. So normally you'd have an x component, a y component, a z component. Here we have an s component, an n component, and an o component. And in the same way in statics, you would sum forces in the x direction, the y direction, the z direction. Here we're going to sum forces in the s direction. Right? So how do we split this equation into S, N, and O components? So here we're going to start by saying we're going to look at the S component of the net force, and that must be equal to the time rate of change of linear momentum in the S direction within the control volume plus the net flux of linear momentum in the S direction across the control surface. And you could also write this for FNN and FNO, right? But we're only interested right now in this quantity along the s-axis. So right now we have FNS, or the S component of the net force, equal to the time rate of change of the linear momentum in the S direction within the control volume plus the net surface flux of linear momentum in the S direction through the control surface. Effectively is what this is saying right here. And like I just mentioned, you could have an FNN equation and an FNO equation. We're only going to look at the s-axis for now. Now, because we have a steady system, we can get rid of this time integral again, right? So this time-dependent integral, we can get rid of that. So now we only have this flux term, this net linear momentum flux in the s direction across the control surface integral. That's the only term that's left. And we set that equal to FOS tilde plus FBS tilde. And what is that? Well, we're basically just saying, hey, the S component of our net force can be broken up into the net outer surface forces in the s direction plus the net body forces in the s direction. So that is the equation we're going to be working with. And again, we have this written here, F tilde OS, total outer surface force on prismatic chip in the s direction. We don't know what that is yet. And F tilde BS, total body force on prismatic chip in s direction. Again, we don't know what that is yet either. Now, on this slide, what we're going to do is we're going to examine the surface forces on the chip. So we're kind of looking at F tilde OS here. What are the surface forces on this chip? Well, we know that in control surface 1, we have a pressure force, and on control surface 2, we also have a pressure force. What's the pressure force along the S-axis on control surface 1? Well, that's PA. What's the pressure force along the S-axis on control surface 2? Well, that's P plus DP times A plus DA, right? Now, we're also going to have pressure forces on these lateral faces. Because this chip is expanding and pressure acts orthogonally to a planar surface, we're going to have effectively an S component of the pressure force, and we're going to have an N component of the pressure force. We don't need the N components of the lateral forces because we're only dealing with our Newton's second law in the S direction. So we just need the S components. If you now look at B here, you'll see here's our PA on control surface 1. Here's our P plus DP times A plus DA on control surface 2. Now we have our lateral pressure forces. And each of those lateral pressure forces is equal to P plus DP over 2 times H times DL. So P plus DP over 2 is basically saying, hey, take a balance of the pressure here, and just say it's essentially uniform across this face. So here it's P, here it's P plus DP, so the average pressure along this face is probably P plus DP over 2. And the area of this face is HDL, and we have that symmetrically reflected on this side too. P plus DP over 2 times HDL. We're going to call that force F, right? And that force is 2 components again, an N component and an S component. Again, we don't really care about the N component now because we're not looking at that. We're only looking at the S component. So Fs is the component in the S direction of these lateral forces F. Now let's look at C. We're kind of spinning this around now. We're looking at it from the side again. So we're looking at our forces on control surface 1 and control surface 2 here. Now you'll also notice that you will have pressure forces on the top and bottom faces. You'll have pressure forces on the top and bottom faces because this prismatic chip is immersed in a broader fluid. However, these top and bottom faces, the pressure forces on these top and bottom faces, are along the O axis. We don't need the top and bottom forces as they act along the O direction. And again, we're only worried about the S direction. So we're ignoring those forces. One thing to note here, if you had friction, you would have something like this. Something like that. You would have friction forces on those faces that would contribute to the force balance in the S direction. And in the same way, here, if we go back to B, you would have friction forces on these faces that would do something like this, and they would have components in the S direction. That would mean that they would need to be accounted for in the S force balance. Now, because we're assuming a frictionless flow, we don't need to include those friction forces because they don't exist. It's frictionless. If we had a flow where friction could not be neglected, those forces would need to be in the force balance for this to yield an accurate result. And you will see that in many flows, in many areas of flows, friction is incredibly important, like in low Reynolds number flows, like in boundary layers, etc. So Bernoulli's equation will not apply and will not give you the correct result when you can't neglect friction, because Bernoulli's equation is, as you see here, completely neglecting friction. It's not accounting for those forces that would be on these faces that you would need to account for in the S force balance. But now we're going to look at D, right? So let's look at D. And essentially, FOS, again, that is the total outer surface force on the prismatic chip in the S direction. We could see that that is PA, right? Because this is positive S in this direction, right? So we have PA minus P plus dP times A plus dA plus 2FS. No friction, no Reynolds stress, nothing like that. How are we going to define Fs? Well, again, we've defined Fs. It is the magnitude of the S component of F, which is this lateral pressure force right here. Here we go to slide 4 here, where we're going to look at our examination of our surface forces on the chip. Now here we have a lot of geometry. I'm not going to go over all this geometry. This is essentially just defining, relationships between our angles and our differential lengths, etc. Obviously, this is here for you to study, but this is essentially mostly geometry. The one thing I do want to go over is this right here. So if you have an outward differential normal area, dA, and you have a pressure that is exerting a force on that differential area, then that differential force is equal to dF, which is equal to negative P hat dA. And that negative sign there is to indicate that the force acting on that differential area is acting in the opposite direction to the outward differential normal. If you have an outward differential normal and you have a pressure force that's acting inwards on that area, the direction of that differential force is opposite of the outward normal. It's inward. And so you have a negative sign to say, hey, dF acts in the opposite direction of dA. Now, if you want to find the component of that differential force dF in some random arbitrary direction, let's say L, the L axis, you just take the dot product on both sides of this equation with the unit vector of that axis. In this case, if we're looking along the L axis, L hat is the unit vector for the L axis. So we take the dot product on both sides with L hat, and you effectively get that your differential force in the L direction is equal to negative P hat times DAL, where DAL is the projection of your differential area in the L direction. So DFL is equal to negative P hat DAL. This is a very familiar set of logic and equations if you've reviewed hydrostatic forces on curved surfaces. So F tilde OS, we've kind of derived this form of the equation already. F tilde OS is equal to PA minus P plus dP times A plus dA plus 2FS. We have a differential force on the side of our prismatic chip, and we want to find the S component of that force because we're trying to find Fs, right? If we go back to the prismatic chip, we're trying to find Fs. We're trying to find the component of this force in this direction. Well, we have an equation for that now. It's this equation right here. So from the equation that we just reviewed, we see that DFS is equal to negative P hat DAS, which is just from this set of equations here, which is just from this set of equations here. Well, what is DAS? I'm going to just kind of drop the tildes. What is DAS? Well, we know from our geometric analysis that DAS, as you see here, is equal to dA cosine of psi, where psi is the angle between dA and the S axis at any given location along this lateral face. Right, so DAS, the S component of the differential area, the S component of the outward differential area on that lateral face is equal to dA, the magnitude of the differential area, times cosine of psi, which is just this angle right here. So we see that we have negative P hat dA tilde cosine psi is equal to DFS. Well, what is our P hat? What is our general pressure? Well, our general pressure on that face we've already established is we're kind of just assuming that it's a balanced and arithmetic average of the pressures on these 2 points, so P plus dP over 2. We have negative P hat or negative P plus dP over 2 times dA cosine psi. And this is equal to DFS, or the differential force in the S direction associated with F. So Fs is equal to the integral of DFS over Fs, definitionally. It's also equal to the integral of DFS over A tilde, which is that lateral area, right? This lateral area, let's see, where is our lateral area here? Our lateral area is this lateral area right here, HDL. Now if we go back to our original diagram here, see if we can kind of cross-reference that. H and indeed DL. So the area is, the height is H, as you can see here, and the length is DL. So HDL is our A tilde. Well, what is DFS? We know it's equal to this quantity right here, which is where that is. Now, we have a lot of constants here. P plus dP over 2, that's a constant. The negative sign is a constant, -1. Cosine psi is a constant. It's a geometric constant associated with this diagram right here. So now we have the integral over A tilde of dA tilde. What is that definitionally? A tilde. We know exactly what A tilde is. It's HDL, right? It's HDL, it's just this area right here. It's this height times this length, it's HDL. So we have HDL cosine psi negative P plus dP over 2. Now, what you can say is that this is equal to P plus dP over 2 HdW. Why is that? Why is that? So let's look at our geometric diagram again. dW is equal to negative cosine psi dL. So if we have negative cosine psi dL, we can just replace this with dW. Now we have a workable expression for Fs. Multiply that by 2. 2Fs, you get 2P plus dP over 2 times dA over 2, right? Why is that? Because HdW is what? dA over 2. How do we know that? We go back to the beginning here. HdW is dA over 2. So we have dA over 2, dA over 2. Now we can multiply by 2, and what do we get? We get P plus dP over 2 times dA. 2Fs is equal to P plus dP over 2 times dA. Now this is really powerful because now we have our F tilde OS, we have PA minus PDA minus DPA minus DPDA plus PDA plus DP over 2dA. How do we get that? Well, we know exactly that F tilde OS is equal to this quantity right here. We have PA, we distribute this, we have 2Fs, which is this quantity right here. We simplify and we get that F tilde OS is equal to negative DPA minus DP over 2 times dA. This is the second sub-equation that we need for our overall force balance. Now we need F tilde BS, which is essentially, what is F tilde BS? Let's go back to our definitions. F tilde BS is the total body force on the prismatic chip in the S direction. We found with F tilde OS the total outer surface force on the prismatic chip, so all the pressure forces. Now we need the total body force in the S direction as well, which in this case is just due to gravity. Again, I'm not going to go over too much of the geometry here. This is here for you to study as you wish. But effectively, if you're looking at the side view of this prismatic chip, it has a weight that is acting anti-parallel to positive z in the direction of gravity, right? Looking at our global coordinate systems. And we have our prismatic chip, which is angled up at some angle theta. And this dz is kind of the leg of this right triangle associated with the control surface 2 surface of the prismatic chip. So FBS is the total body force in the S direction. We can kind of see that if we draw our O-axis and our S-axis, you could see that there's a component of W along negative S and along O. We don't care about the O component, right? We only care about the S component, and it's negative. It seems as if it's negative according to our depiction in the free body diagram. So FBS then is just equal to negative WS, or negative the S component of the weight. So with that being said, we have that negative WS is equal to negative cosine of 90 degrees minus theta times W, which is equal to negative sine of theta through a trig identity times W, which is the integral over the volume of rho g dV. We simplify this integral, and we see that FBS, or F tilde BS, is equal to negative rho g times the quantity, A plus dA over 2 times dz. Now we just have this linear momentum term, right? Integral over the control surface of US rho v dot dA. We're going to explicitly look at every control surface we have to kind of hit home why these other surfaces are 0. But effectively, we're only going to be looking at control surface 1 and control surface 2. Now, for control surface 3 and 4, which we could say are the sides, and control surface 5 and 6, which we could say are the top and bottom, the velocity and dA are always at a 90-degree angle because the control volume is bounding the streamlines on the top and bottom and on the sides. So dA, the outward normal, and the velocity, which is just the velocity of the fluid, at every given point along the sides and the top and bottom always have an angle to each other of 90 degrees. And so V dot dA at every point along the sides and top and bottom is equal to 0 because they're always at 90-degree angles to each other, V and dA. So because V dot dA is equal to 0, control surface 3, 4, 5, and 6, those sums, those integrals are equal to 0. As a result of all of that, you only have the integral over control surface 1 and the integral over control surface 2. If you actually break those down, you can see that the integral over control surface 1 Vs rho v dot dA plus the integral over control surface 2, Vs rho v dot dA, is equal to this algebraic sum here. Because the velocity and the pressure, most relevantly the velocity in this case, is constant along control surface 1 and control surface 2. As a result of that, these integrals can break up into these algebraic sums. So you have Vs1 rho Vs1 dot A1 plus Vs2 rho Vs2 dot A2. What is Vs1 dot A1? Well, that's just equal to negative Vsa, right? Because for control surface 1, the velocity is going up, the outward area is going down, so to speak, and so we have negative Vsa. We have our plus sign here, and then we have Vs2. What is Vs2? Well, it's Vs plus dVs, right? Because that's the velocity at control surface 2. We have our rho. What is Vs2 dot A2? Well, Vs2 is essentially on control surface 2, the velocity is pointing up, and the outward area on control surface 2 is also pointing up, so to speak. So that dot product is positive. So we have Vs plus dVs times A plus dA, because the area of control surface 2 is A plus dA. So Vs2 rho is this right here. Vs2 dot A2 is this right here. So we have this sum is our linear momentum flux term. When we simplify that, we get negative rho Vs squared A plus Vs plus dVs times rho times the quantity Vsa plus Vsda plus dVsa plus dVsda. This is a real big blocker because we're not quite sure what to do with all these terms. However, from conservation of mass, if you remember, going all the way back now to conservation of mass, we got this equation, which basically just says along the prismatic chip, within the prismatic chip, mass is conserved. Well, look at that. This is the same exact grouping of equations as conservation of mass gives us, and we know that that is equal to 0. So all of this whole sum goes to 0, which is great because now we have negative rho Vs squared A plus, essentially distributing this, rho Vs squared A plus rho Vs A dVs, and we don't have to worry about any of this. This all goes away. So we just take this right here, and we algebraically distribute and simplify it. You do that, and the result of this linear momentum flux term, integral over the control surface of us rho v dot dA, is just equal to rho Vs dVsa. That's all it's equal to. Now, if you go and you combine all of these terms, so you have Fns, which is just equal to Fos tilde plus Fbs tilde is equal to the linear momentum control surface flux term, integral over the control surface of Vs rho v dot dA. You plug in all of the results. So you have negative dPa minus dP over 2 dA minus rho g times the quantity A plus dA over 2 dz is equal to rho Vs dVsa. Again, mapping just like this. And you simplify this, you get that Fns is essentially equal to negative dPa minus dP over 2 dA minus rho g A dz minus rho g dA over 2 dz, which is equal to rho Vs dVsa, right? This is just a simplification of this right here. Now, if you divide by rho A, which you can do, because again, we're assuming we have a constant density flow, so rho could be taken out of integrals, it could be divided out, it could be very easily manipulated. And the only reason we can do that again is because we're assuming density is constant. Now, if we assume that the products of differentials are negligible in comparison to the remaining terms, so for example, when you divide by rho A, you get some terms like negative dP over rho, okay, minus dP dA over 2 rho A. Well, dP dA is the product of two differentials. That's going to be really, really, really small compared to something like negative dP over rho, which only has one differential. So dP goes to 0 very quickly. dP dA goes to 0 incredibly quickly. And so if dP is really small, dP dA is incredibly small, right? So we're essentially saying the product of differentials is negligible in comparison to non-product of differentials. So we'll just let those go to 0, essentially, because they're really, really small. And the result of that is the outcome of this simplification is negative dP over rho minus g dz is equal to Vs dVs. What does this equation say, really? It's effectively the mathematical expression of Newton's second law in the s direction for this prismatic chip, or conservation of linear momentum through the prismatic chip in the s direction. So now that we have this differential equation here, what we want to do is integrate along the streamline. So if you have this position 1 and you have this position 2, and you have a fluid parcel that kind of travels from 1 to 2 along any arbitrary path, that arbitrary path can be discretized into a large number of these prismatic chips that we have described previously. And we know that along each of these prismatic chips, this equation applies. And this equation has to apply along each prismatic chip because this equation is Newton's second law, and Newton's second law has to apply at every point in the system. So what we end up having then is we could say, well, if we sum all of these equations over this entire streamline, so for example, we take this left-hand side and sum it along 1 to 2, and then we take this right-hand side and sum it along 1 to 2, those sums should be equal to one another. So essentially what we're saying is, let's integrate this left-hand side from 1 to 2, and then let's integrate this right-hand side from 1 to 2. And that's essentially what we get, and effectively that's saying, along this streamline from 1 to 2, Newton's second law has to apply at every single point along that streamline, which we know to be true. So if we integrate the left-hand side from 1 to 2, and we integrate the right-hand side from 1 to 2, we get this integral right here, which is very akin to the kind of integral you might see like a separation of variables technique in differential equations. And when you perform this integral and simplify, you end up getting this equation right here, which says P1 over rho plus GZ1 plus V1 squared over 2 is equal to P2 over rho plus GZ2 plus V2 squared over 2. So again, we have a pressure term, an elevation term, and a velocity term on both sides of the equation. So now if we go forward, we'll get to our final Bernoulli's equation result. We'll see that Bernoulli's equation is commonly expressed in one of two ways. The first way is P over rho plus Vs squared over 2 plus Gz is equal to constant. Or the second way, which I'm more familiar with, is P1 over rho plus V1 squared over 2 plus Gz1 is equal to P2 over rho plus V2 squared over 2 plus Gz2. And essentially what this is saying is, if you know the pressure at point 1, you know the velocity at point 1, you know the elevation at point 1, you know the pressure at point 2, you know the velocity at point 2, you know the elevation at point 2, you know an equality that will hold between those 2 points, right? And it is this equality right here. So the nice thing about this is very often you'll know what V1 and V2 are through conservation of mass. You'll know what GZ1 and GZ2 are through the geometry of the problem. And you'll know what P1 is maybe because you know the driving pressure. That allows you to solve for P2, what the pressure is at the downstream side of that streamline. And there are other permutations that are equally as valid. For example, like maybe you know P1, V1, Z1, P2, and B2, and you need to solve for Z2. How high does the streamline go? Or how low does the streamline go, etc. This is a very, very, very powerful equation, but it must adhere to the following assumptions as we referenced earlier. For example, some of the most fundamental assumptions here, we've seen them throughout the derivation. Assumption 1, we have steady flow. The variables, the flow variables, the field variables are non-time dependent. 2, we have flow along a streamline. We have flow along a streamline from point 1 to point 2. 3, we have negligible viscous shear. In other words, we have negligible friction. And we also have negligible other surface forces, for example, Reynolds stress. 4, you have a constant density flow. In other words, incompressible and isothermal. And 5, the only body force is gravity, for example, no magnetic or electric fields. So for our final slide, we're just going to have some simple guidance here. And it's worth mentioning that the best way to develop this intuition is to just do a bunch of example problems. So let's go over a few examples of reasonable applications of Bernoulli's equation. For example, if you're looking at a system and you're viewing it through the lens of Rand's equations, or Reynolds averaged Navier-Stokes equations, and you're examining streamlines, mean streamlines in those Rand's systems. An example of a reasonable application of Bernoulli's equation may be a steady, free stream, mean streamline in a high Reynolds number liquid flow with negligible turbulent kinetic energy. So in other words, steady, so steady, mean streamlines, so streamlines, high Reynolds number, so negligible-ish friction, at least relative to other forces, liquid, so constant density, and negligible turbulent kinetic energy, meaning negligible Reynolds stresses, meaning negligible other surface forces that aren't pressure. Another example might be a steady, open channel, free stream water flow with negligible channel wall friction. So now let's go over some examples of unreasonable applications of Bernoulli's equation. 1, constant diameter, straight pipe flow. If you have a constant diameter straight pipe and you look at a streamline right down the center of that constant diameter straight pipe, the elevation's constant, the velocity's constant because of conservation of mass, and therefore, according to Bernoulli's equation, the pressure's constant. But we know that's not the case. We know that in a case like that, the flow will lose pressure per unit length along the pipe. Why is that? Because friction is typically not negligible within internal flows. So, for example, pipe flows, friction is typically not negligible. So there's typically friction that has to be accounted for in flows like this, internal flows. And so Bernoulli's equation very often does not apply unless it's a very special case. So you need a different set of equations that accounts for this new surface force, friction. And for example, in pipe flow, you would use something called the fluid energy equation, which will be another video. A second example is orifice flow. Typically, orifice flow is associated with a lot of friction. So for example, as the streamlines compress into the orifice and then expand out of the orifice again, that compression and expansion of streamlines is associated with a high degree of friction, and that amount of friction is typically not negligible in the flow field. And so if you apply Bernoulli's equation to an orifice flow problem, you will probably vastly overestimate the amount of flow you'll get for a given pressure differential. Now, that doesn't mean Bernoulli's equation is not useful for orifice flow problems. It can be useful in the sense that it can give you a thermodynamic or theoretical maximum flow rate for a given pressure differential. So for example, let's say you have a problem where you need 5 liters per minute out of an orifice, and you've designed an orifice and you've designed a pressure differential. You apply Bernoulli's equation to that orifice and it says, hey, at that pressure differential you get 4 liters per minute, but you need 5. What that's saying is it is physically impossible to get 5 liters per minute out of that orifice with that pressure differential, because that is the amount of flow you'd get with no friction, and no system is frictionless. Friction, adding friction to the system, will reduce the flow you get for a given pressure differential. So in that case, you would just know, okay, this orifice, this pressure differential is just physically impossible in terms of getting the flow I need. So it can give you a theoretical maximum, and that basically indicates to you I need to change the orifice, I need to increase the pressure differential, etc. Now, if you're in the realm of possibility and you're looking for an accurate model of how much flow you actually get through the orifice, Bernoulli's equation is probably not going to get you there. You're going to need something else like the fluid energy equation or CFD or something to that effect. Now, with all that being said, the next step is we're going to go into some example problems that kind of teach us how to use Bernoulli's equation and the situations in which Bernoulli's equation is appropriate. Now, this particular derivation of Bernoulli's equation through Reynolds Transport Theorem is not super rigorous. It's very abstract, it's very mathy, and it's kind of hard to follow at times. But the reason I like it is because it really emphasizes how important the assumptions are in the derivation of Bernoulli's equation. It's very easy to draw lines between the assumptions that Bernoulli's equation requires and steps in the derivation. The next derivation we do of Bernoulli's equation using Newton's second law is far less abstract, is far less mathy, is way more mechanically intuitive, and it is more rigorous. So, with all that being said, thank you very much for listening. I really appreciate you watching, and I will see you next time.